Hello, calculus students. This is Mr. McAllen, and I'm going to be talking to you today. This is the third video on linearizations. And what I want to talk to you about today is imagine if I had you in class and I asked you, can you approximate for me the square root of 99? And a lot of people would say, without calculus at all, they would say, well, it's got to be less than 10 because I know the square root of 100 is equal to 10. And I would say, well, that's really smart. That's a good way to approximate something. But let's say that we need to get a really good approximation, better than just a rough guess. We can use calculus through the use of a linearization to find a better value. And what we're going to do in this video is we're going to show you how, with that linearization that we talked about in the earlier videos, you can actually find a really good approximation, and we're going to actually measure and see how good that approximation is. But when you decide to do that for something like the square root, we need to understand a few things. Like, first of all, in this linearization, what is this a value? And how are we going to use that a value? And what is the x value? What does that pertain to? Because you need to know what these values are, so that you can figure out the function. You also need to know, for the square root of 99, what is the function? There are calculus books where they just say, approximate root 99 using a linear approximation, and they don't tell you what the function should be or where your approximation should be centered at. In this video, I want to help explain that. So, just like we said before, when you thought about what the square root of 99 would be, and you went to what the square root of 100 would be, that kind of told you that the function should just be the square root of x. When you decided to choose the 100 as your value to figure out what the exact value of root 100 was, you kind of figured out that your a value, the appropriate a value, should be 100. The x value is the value that when you plug it into linearization, you should figure out what the linearization at 99 would be, and that's what our x value is. So x in this case is 99. So using the information we had from before, we're going to find the linearization function first. We're going to find f at 100. We're going to find the derivative at 100. And we're going to use our x value, our center point value, to be 100. So doing a little bit of calculus, since our function is equal to root x, I know my derivative is equal to 1 over 2 root x. And I can now figure out that f at 100 is equal to 10. My derivative at 100 is equal to 1 over 20. And my linearization now becomes 10 plus 1 over 20 times x minus 100. So if you want to use this linearization to approximate the square root of 99, well, you can. You just plug in 99 for x, and you end up getting 10 minus 1/20th, which 1/20th is 0.05, and you would end up getting 9.95 as your linear approximation. Let's see how close that is in real life. I have a tool called Desmos, and I'm going to put in the square root function. I'm going to look at it at, now Desmos is a free app, and what we can do with Desmos is we can, I'm just going to change these functions, the ones that we're using, and this is a little table that I use, so I'm going to put in the function f of x, if I can type, is equal to the square root of x. I'm going to put in my linearization. Capital L of x is equal to 10 plus 1/20th of x minus 100. So I have to zoom out so I can see the functions. And you could see here that um, this is my square root function, and here's a linearization. But if we go all the way out to, remember where the linearization is being done at, it's being done at 100. So I have to go all the way out to, I'm at 50 now. So I'm going to hurry up and get out to 100. And you could see that when we get to 100, you can see the tangent line here, and you can see the square root function here, and you can see at 100 we have pretty good accuracy between the function, or I want to say becomes very linear right here, because you can see that that's the point on the parabola. But if I put in on my table here, if I put in the value of 100, you're going to see that the function and the linearization have the same value. But if I put in 99, you're going to see that as we described earlier in the video, the function value is 9.95 for the linearization, but we have some error between the actual function. And how much error? Well, you would just subtract the two values and do a relative error calculation, and you'd find out that the error is pretty small. It's about it starts to deviate in the hundredths column for the number. So you can figure out, if you want to do a relative error calculation, you can figure out what percent error you had between them. But you can see when we zoom in here that the difference between the two functions is pretty small between the two of them. Um, they're right on top of each other at 99. Oh, and if we keep zooming in, we can maybe see the two values break away. Here we go. Now we're starting to see the error between the one point and the other. And if you look at the error between them, you can see that zoom in close, there's definitely significant error when you look at them up close. But when you consider them in a relative sense, it's far under anything appreciable at this level. When you zoom out, you can see that the approximation is in fact pretty good. So anyway, not to make this video too long, but I just wanted to share with you how you calculate that approximate value with a linearization, and how you want to make sure that you pick an appropriate value. So what I'd like you to do is, I would like you to try to approximate the value of the square root of 4.25 using this linearization, and pick the appropriate point and pause the video, and I'm going to have the solution up when you unpause the video. Square root of 4.25. Okay, and we're back. And so we're approximating the square root of 4.25. The center point is at 4. The value we're going to use in the linearization will be 4.25. Again, the function is a root function. The derivative same as before. Center point function value, f at 4 is equal to 2. The derivative at 4 is equal to 1/4, plugging into the derivative. Plug in to your linearization. You get 2 plus 1/4 is a derivative. You plug in 4.25. When you work through all the computations, you find out that the root of 4.25 is approximately 2.0625. And on the calculator, if you try it at home, 4.25's value is, I'm just going to do it on the calculator I have right here, 4.25, and I get 2.01, I'm sorry, 0.6155, and then more decimal places. But you can see how close the two numbers are, and they're relatively close. And we could do, again, another relative error calculation. But hopefully this video has helped you see the use for a linearization to approximate a function. Have a good day.